Hey everyone, in this activity we're going to be learning about data transformations and data manipulation with the dplyr package. So to start, data that we often encounter in class comes in this nice tabular format where we have rows and columns. And this makes it much easier to make visualizations with, to obtain summary statistics for, to fit models, and to do other data manipulation operations. But the reality is, when you encounter data in the wild, so to speak, in your real job, it often can come in a much messier format. So for example, here, you can see in the graphic, although it's a little bit small, but ideally we'd have data like this, the Palmer Penguins data set in the top, where we have well-defined variables and rows constituting repeated measurements on those variables. But sometimes, for example, in the bottom table here, this is a data set I had for my first project in grad school, where it's given as an Excel file, and you maybe have some hierarchy in the data that's represented with different rows. So these are actually supposed to be additional columns or variables in the data set, but they're encoded using rows spanning multiple columns. And we have highlighting that's representing an additional variable here. Okay, or you have blanks because the value is assumed to continue from what the most recently observed value was. So it can come in a much messier format that takes some non-trivial amount of efforts of data cleaning in order to clean that up. And this is where our packages like dplyr can help us out to make this data cleaning and process of getting our data ready for analysis much easier. So some estimate, reading around with blog posts and some slightly unscientific studies that people have done, but people estimate that roughly 50 to 80% of the time data scientists spend in their jobs is actually just trying to prepare the data for analysis to get it in a nice tabular form or other structure that's more conducive to making visualizations or obtaining summary statistics. So this is not the flashiest or most exciting part of statistics, but it's a very necessary step to being an effective and successful data scientist. So that's what we'll be covering in this activity, is learning about a lot of the methods available from the dplyr package to do this. So specifically, we'll look at how we can subset to particular rows using the filter function, how we can rearrange rows or observations in a data set with the arrange function, how we can rearrange columns or drop columns with the select function, how we can modify or create new variables in our data set using the mutate function, and how we can calculate summary statistics for different subgroups in our data using the group by and summarize functions from the dplyr package. So data visualization, which we've learned about a little bit with ggplot2, is very useful, but a necessary step in order to make effective data visualizations is to have that data in a format that's ready to go. So what we're going to look at in this activity is a data set on flights out of the four largest Michigan airports. This data set has every flight included that left a Michigan airport between 2019 and 2021 inclusive. And the four largest airports are Detroit, which has a code of DTW, Lansing, LAN, Grand Rapids, GRR, and Flint, FNT. So I obtained this data using the AnyFlightsR package, which allows you to query data about flights that left airports in the United States. Okay. So there's lots of variables in this data set. Here I have most of the ones that will be relevant for this activity, so the variable names, and then a description of the variables. So this is what we call a data dictionary, a table that describes variables in the data set that we're working with. So first, before we look at this data set, let's load some packages that we'll need for this activity. So just like usual, you may need to install one of these packages if you don't already have it installed. Otherwise, let's make sure that we can load this. The tidyverse package has many sub-R packages contained in it. The dplyr package is one of those. So by loading the tidyverse package, we are loading dplyr among other packages like ggplot2. So hopefully everything loads okay. The mice package will help us with methods for dealing with missing values, and the nannyR package is made to help us work with missing values as well. Okay. So we'll look at some of those as well. So next, we'll import the data from a CSV file that you can obtain via Blackboard and import it into R, creating an object called MIFlights. So you'll have to download this file that's contained in a zipped file. And then once it's in your downloads folder, you will have to decompress the file. On Windows 11, I do that by right-clicking on it and clicking Extract All. It'll be slightly different on older versions or different versions of Windows and slightly different on a Mac. But the idea is we're going to decompress this file, which then creates a folder, and this has the CSV file in it. Okay. Now let's import this data into R, and we're going to use the read CSV function to do this, which is made available after we load the tidyverse package. So make sure you run this code to load these packages. Okay, and we're going to have to find the right file path to put inside read underscore CSV. This file path will differ slightly depending on everyone's own laptop. Okay, in my case, one way to find that is to use the file.choose function. If you submit this to the console, it should have a pop-up window. And, oh, actually, mine doesn't work the best, but there's a little bit of lagging here, but I think that's just an issue on my own laptop. So if you navigate to the file using file.choose and select it, it should print out a full file path to your data file. Copy that, including the quotes, paste it here. Okay, and then you should be able to run this and import the data set. It takes a little bit of time. Gives us some messages about the number of character variables that were read in, number of numeric or double type variables, and the number of date time variables. Okay. But after you import it, you should see this object called MIFlights in your environment pane that has 463 or 464,000 rows or observations and about 37 variables or columns. Okay. So now that we've successfully imported the data set, next let's use the skim function to acquaint ourselves with it and look for patterns of missingness and explore other patterns in this data set. Okay. So skim is loaded or available since we loaded the skim R package. And as a reminder, this looks best when knitting to HTML. Skim does. So let's knit the document and take a look at what skim shows us here. So we have lots of variables going on. This is where skim can really help us out. Again, number of rows, number of columns. And then skim gives us summary statistics or a high-level overview of the variables organized by the types of variables. So for the character variables here, and I did not fill in missing values for this data set, so this is more realistic for how data tables can come. Here we have a lot of missing values, okay? For the tail number of the plane, there's 2,200 almost missing values. But notice that when rounded to 2 decimal places, it's saying it's 100% complete. Okay. There's 5,200 roughly unique tail numbers for the planes. We have over 11,000 missing values for different characteristics about the machine of the plane itself that flights were on. Okay, which may sound like a lot, 11,000 missing values, but in the grand scheme of this data set, in this setting, 98% of the values are still complete or non-missing. So actually not too bad. Looking at the numeric variables real quick, we can look at patterns of missingness again. We see most of the variables have nearly all the values being non-missing. Departure time is missing for 9,000 flights. Again, that might sound like a lot, but in the context of this data set, 98% of the values are non-missing, so not too bad. I would still make note of it if I were analyzing it in, say, a data science interview or giving a report on this to a supervisor, but certainly could proceed still using this variable for analyses without much of a problem. Although the missingness patterns would maybe want to be investigated further. So that goes for all these variables that have like 98% missing. Okay, I'd maybe do a little bit of digging, but not too concerned about it. Here's where we have some concerns with missingness. Some of these variables that describe the weather going on when a plane departed from an airport have a lot of missing values. So the temperature, the recorded temperature, only has 5% of values being non-missing. 95% of the values are missing. This is a good case of a variable I wouldn't touch with a 10-foot pole, as they say. There's way too much missing values here to make strong conclusions or to make any conclusions really without far too many caveats or limitations to what we can say. The patterns in temperature could be drastically different if we had most of the data here, so it's too difficult to make any strong conclusions. These would just need to be looked into further to say, where do we have non-missing values? Where is the missingness occurring? And why is this happening? Okay. But some of the weather variables are nearly all there. It looks like measurements about wind, 98%, 99% complete. That's much better. We can probably do something with that, the amount of visibility. Okay. Another quick thing to skim or look at, the min and max values are always good to check. For year, the minimum value is 2019, the max is 2021. That's just like we expected here. Okay, if we saw something outside this range, that would be a little concerning. Same with the month, goes from 1 to 12. Okay, that's the month of the year. So again, that is like we would expect. Day 1 to 31. Okay. Right. You can see departure time goes from 1 to 2,400. And delays, okay, depth delay is the number of minutes a plane left behind schedule, with negative values indicating that the plane was early, it left early, and positive values indicating that the plane left late. So the earliest any plane left was 54 minutes early. That's super early. But the median, 50% of the time, a plane leaves 3 minutes or earlier. That seems about right. 75% of the time or more, a plane is right on time or early. Okay, but the worst any plane left was about 2,700 minutes late. And although very extreme, it's technically possible, we suppose. So something went really wrong for those people on that flight, unfortunately. Okay. Similar values looks like for arrival delay. We have the distance of the flight in miles, the number of minutes the plane was in the air in minutes, the amount of time the plane was in the air in minutes. Okay. So a good chance to check for different patterns in the data. If you notice the plane speed variable, the min value is 0. The 75th percentile is 0. So 75% of values were 0 at least. Okay, at least 75% of values were exactly 0. And it looks like there's a max of 438. So something strange is going on with that variable. I did some digging on my own. It's supposed to represent like the peak speed a plane can achieve, I believe, in miles per hour, but it seems like for many of the planes, it was just recorded as 0, effectively a missing value. Okay, so we'll know that we need to ignore this variable later on because it was not encoded properly. All right, so that's just a quick look at skim here. Yeah, we talked about how many variables, how many observations. We just talked about missingness. Now let's make a bar chart showing how many flights went out of each of the major airports here. Okay, we'll do this using geom_call. We're going to use the count function along with geom_call. You can make a bar chart using geom_bar, but you can also make a bar chart using geom_call and ggplot. So we're going to look at this way for how to do it, although you could do this with geom_bar as well. So let's take mi flights. We're going to pipe that into the ggplot function. Okay, but first what we're going to do is we're going to pipe it into the count function from the dplyr package. So we're going to count up, since each row in this table of data is for a single flight that went out of an airport. Okay, if we look at the origin variable, this gives the source airport, where the plane was flying out of. So if we count the number of instances of DTW, for example, that tells us how many total flights went out of the Detroit airport. So the count function from dplyr allows us to tally up the number of rows that have a certain value of a categorical variable. In this case, if we look at this by submitting this to the console, we can see that that tallies up the number of flights that left out of Detroit, the number of flights that left out of Flint, Grand Rapids, and Lansing. So this creates a new table of data that just summarized our original data set that has two variables, the name of the categorical variable, origin, and then lowercase n that gives the count. geom_call allows you to make a bar chart such that you have a variable for categories determining the bars, in this case origin, and you have a variable that determines the height of the bars. In this case, the variable n is what will determine the height of the bars. So x, we're going to have it be a vertical bar chart, is origin, because it's specifying the group for which the bar belongs to or represents. And then y, our vertical axis, is going to be given by n, because it's matching this variable name that is spit out from count. Okay. If we add geom_call to this, a geom_call layer, this will make our base bar chart that we're going to pretty up a little bit. Okay. But out of the box, we've already got a bar chart going. So we have a bar for each origin airport. We have the count of the number of flights. Notice that it gives it to you in scientific notation. This is saying 4 times 10 to the 5th power, 3 times 10 to the 5th power. Okay. We never want to report a visualization with scientific notation. Even for those with math backgrounds who are familiar with scientific notation, it takes extra time in our heads to do that little bit of conversion, and it's just inefficient and sort of is contradictory to the idea of data visualizations efficiently and effectively communicating aspects about our data. So we always want to avoid scientific notation, unless we have a very strong reason otherwise. Okay. So let's sort the bars by descending height using the factor reorder function. So we can do this inside of AES. What we're going to do is say FCT underscore reorder. Okay, and then inside FCT reorder, we're going to say we want to sort origin by n, and that we want it in descending order. So we're going to say dot DESC equals true. Okay, now you notice if we rerun the code, we will then have the bars sorted in descending order. Since the airport origin is a nominal categorical variable, that is, there's no natural ordering to the categories, we always want to sort that type of bar chart by height. Could be ascending, could be descending, but we want to sort by height because that helps more efficiently communicate which group was the largest, which group was the smallest, and doesn't leave any ambiguity or guessing in between. For example, Flint and Lansing are so close, we want to order these bars based on height to make it clear that Lansing had less flights. Okay. All about communicating data, aspects about our data efficiently when we're making data visualizations, right? So we would only sort it in a different particular order if we had an ordinal categorical variable where there was a natural ordering to the categories. In this case, we don't really have a natural ordering to the airports, so sorting by the height of the bars is best. Okay. So now that we've resorted the bars by descending height, let's clean up this visualization a little bit. Okay, so what we're going to do is we're going to add some labels to the plot. And just like usual, we're going to add a caption that describes the data source. So the AnyFlights R package. Okay, we add those labels. Nice. Now let's get rid of that scientific notation. So here we're going to do that using a scale y continuous layer. And to suppress scientific notation, we can say labels equals scales label underscore. And if we have the scales package installed, we can use this syntax to then label underscore. Oh, I forgot some parentheses here. Okay. If we have the scales package installed, we can use this syntax to then have the y-axis formatted properly. The scales package allows for all kinds of formatting of axes in a nice, efficient manner with a small amount of code here. You can format axes to have a dollar format, or you can use a different symbol besides the comma for thousands. It's other countries might use a different syntax, right? A different structure for this. You can like have euros or other forms of currency as well besides US dollars. The scales package provides a lot of nice options for that. What we're also going to do is get rid of this extra superfluous space between the bars and the axis here, because 0 is the lowest possible value for the number of flights. This is unnecessary space, and we want to get rid of it. So we can do that inside the scale y continuous layer as well by adding an expand equals expansion option. This, as a reminder, says expand the limits of the plot by 0% at the bottom, so 0% below the bottom of the bars, and 10% above the tallest possible bar, 10% of its height. Okay. And so if we run that, now we can see we got rid of that superfluous space. And then the last thing we'll do is we'll just add a complete theme to just pretty up our plot a little bit. You can add whatever complete theme you want. I personally like the theme view option from the GG themes package because it gets rid of a lot of ink in the background of the plot that's unnecessary. Okay. So note that you could color the bars if you wanted, although depending on your goals, it may be unnecessary. And so some argue that for visualizations, you should only use color when necessary, as it can be distracting, but it's a personal preference again. And as long as if you use color, you just want to make sure you use it consistently throughout your report. So if you use a blue for Detroit, a green for Grand Rapids, for example, you would want to consistently use that same blue for Detroit that shows up in any visualizations and green for Grand Rapids in any visualizations. Okay, so consistency is key. So there's our bar chart. Now we can show real quick how we can remake the same bar chart using the geom_bar function. So go ahead and pause your video and try to reproduce this bar chart that we just made exactly the same, but using the geom_bar function. And then after you unpause it, we'll look at it together. Okay. So hopefully you were able to try that out. Let's take a look at how to do this with geom_bar now. So the best place to start is to copy the code entirely from the previous code chunk. Okay. When we're using geom_bar, it actually implements the count function from the dplyr package underneath. So we don't need this intermediate step here anymore. We're going to change geom_call to say geom_bar. And then instead of using factor reorder around origin, what we're going to do is we're going to use fct in freq around origin. So we do this slightly different to sort the height of the bars. Okay. And let's take a look at how this looks now. Oops, have a little bit of an error. Okay, let's see what I did wrong here. So for geom_bar, we only need to specify an X aesthetic. We don't want to specify Y. That's only for geom_call. Okay, there we go. And see how it's the same exact plot from before. The code is very similar, okay? But it's not that one's right or wrong. Either approach works here. Just know that geom_bar is more exclusively used for making a bar chart with a count of a categorical variable, okay, for the different categories of a categorical variable. Geom_call is more general because you can have the height of the bars be any variable that is describing a numeric characteristic about a category. So here it was a count for the number of flights. You could, for example, have the average delay of flights out of each of the airports and have the height of the bar be the average delay in minutes. We would use geom_call for that type of plot. We would call that a bar plot. But geom_bar cannot create that type of visualization. Geom_bar does tallying up of the number of rows in the data for a particular variable. Okay, so that's the difference between the two. Geom_call is more general, can be used in a variety of settings. So it takes a little bit more code to get a bar chart, but geom_bar is a little bit shorter code for this purpose, but it's more limited to only making this type of bar chart for a count. Okay. So when we imported the data into R, we saw a few different types of variables. And we can see that if we use the glimpse function here. So if we use glimpse around MI flights, okay, glimpse gives you a preview of the values for the different variables, which is kind of helpful. Number of rows, number of columns. Gives you very similar information to skim, but a little bit different because skim doesn't give you a preview of the data. So this can be helpful. It tells you the type of the variables in a slightly different way than skim. It says DBL, which stands for double or numeric type. CHR for character string type. DTTM for date time values. Okay. So there's other types of variables you'll encounter in R as well. INT stands for integer, which has to be numbers like -2, -1, 0, 1, 2, 3. Those are all integers. R will sometimes, if it recognizes it's not just a general numeric type, like there's no decimals, it needs to be integers like that. R will store it as an integer type, which takes up slightly less space underneath than a double type. Doubles are when we have decimals, okay? So we can have fractions. It takes up more space for R to store that, so it's not used ideally if it's an integer, but for most of the time, your data sets are small enough that it doesn't matter the difference between the two. Okay, but they just have slight differences like that. Character is a character string value. Okay, so like the origin of the airport, that is a character type variable, although technically it could be stored as what's called a factor type variable. Factors are categorical variables that have a fixed possible set of values. So in the case of the airport, since there's only 4 possible values, okay, the Detroit, Grand Rapids, Flint, Lansing, this could be encoded as a factor variable with 4 levels, okay? And that can take up less space than a character string variable because in the data, although it's stored as a character string right now, if you stored this as a factor, instead, what R will do is it creates a numeric encoding of the values underneath, although it will still display the labels as they are. So for example, if we coerced origin to a factor, okay, we can see. See if I can do this properly. Okay. Yes. So I coerced origin to a factor here, not permanently in the data set, but just in the console. And it still looks the same for the most part, but now it says this is a factor variable with these levels. R recognized, oh, there's only 4 possible values. And so underneath what it did is it numerically encoded these as 1, 2, 3, and 4, essentially encoding it as an integer. So it takes up space like an integer would, which takes up much less space on your laptop than a character string value does. So it's more efficient space-wise. Okay. Again, most of the time, and there's other slight differences as well between a factor type and a character string type, but for the most part, our data sets won't be big enough for it to matter. Okay. LGL stands for logical, also sometimes called Boolean values. These are values that take on 2 possible values, true or false. Okay, and these take up very little space in R. So if you have something that is a binary variable, this can be helpful to store it as a logical variable. And DTTM stands for date time. These are a richer type of information because date times behave similarly to numeric types, also in some ways similar to character strings. Date time values can, let's see, if we look at this, where's the date time value that we have going on? Time hour, okay. When you hover over variables after opening it up in the table, R will tell you some things about it, like is it numeric? Is it character string. With the date time values, it usually says unknown in my experience for some reason. But this is a rich type of information. So it has the year, the month, the day, hour, minutes, second component. So it has lots of different attributes that we can extract. This behaves similar to numeric in that we can sort this column. If you click on it, you can sort this. But it also has different attributes you can extract out of it, like the year component we could take out of this variable. The month component, the day component. There's a particular day of the week that this date fell on. Say it was, not sure what December 31st, 2021 was, but it might have been a Wednesday. We can extract that attribute about it, knowing that this was on a Wednesday. Okay, so it's a richer type of information than, say, just a numeric type, but it behaves similar to numeric. So date time values are a little bit complex, and we'll learn about them in a different activity. So that's a bit about the variable types, just briefly. Next, let's talk about some of the key functions from the dplyr package. So the dplyr package has many functions that are useful for summarizing or organizing our data in a way to prepare it for visualizations or analyses. We'll cover some of the most useful and commonly used functions here: the filter, arrange, select, mutate, summarize, and group by functions. So base R essentially R that you can use out of the box without loading any additional packages like the tidyverse has methods for all of these same operations. But by installing the tidyverse and loading this package, these developers have made functions that we can use for these different data operations that work in a consistent manner and are a little bit more user-friendly. So when developing the tidyverse and the dplyr package, the developers tried to have consistency in mind by making the first argument always be a data frame or a table of data, and subsequent arguments being for customizing aspects of what the function is doing to that data frame, typically using variable names without quotes. The result of every one of these dplyr functions is another data table that is spit out and can then be piped using this pipe operator into subsequent dplyr functions. Okay, so this allows us to chain together multiple function calls to make our code more readable, and it also can be more efficient in running faster. So let's look at filtering rows with the filter function to start. So filter can allow us to subset observations of a table of data. So let's start by subsetting to only flights on January 1st in this data set, creating an object called janFlights. Subsetting to flights on New Year's Day. So to use the filter function, the general structure is you give your data set type, and we're going to use the syntax dplyr : filter, since filter is a common function name. So we want to make sure we get the right filter function from the dplyr package. And then you have a condition where this should evaluate to a true or false condition based on some function of variables in the data set. And if it's true for each row, it will keep those rows. If any rows return false, it will drop those rows or not keep them in the assignment of the janFlights object here. Okay, so in this case, our data is mi_flights. And our condition is that we want the month to be equal to 1, and we use 2 equal signs to check equality in R, and we want the day to be equal to 1. Okay. If we run that, we can see in this code that we have 1,037 flights that departed on New Year's Day. And you can click it and open it up and see and confirm that all these flights left on New Year's Day. So notice that when we have multiple conditions we want to be true inside filter, we can separate them with a comma. And this requires that both of these conditions are true to retain that row. So it serves as like an and. We need the month equal to 1, and we need the day equal to 1 to keep that row. Let's try this again. So let's get flights that left on Christmas Day, December 25th. So maybe try this on your own. Maybe pause the video real quickly and try this on your own before I show how to do it here. Okay, to show how to do it, so let's subset to flights on Christmas Day. And we're going to call this December 25. We want month equal to 12, day equal to 25. And so we can see that 906 flights left on Christmas Day in this data set. So notice that MI flights is staying the same. It's not losing rows. So when we have a pipe chain and we pipe a data set into other functions, what R is actually doing underneath is creating a temporary copy of the table at the start of the pipe chain and modifying that temporary copy. In this case, it's dropping rows from this temporary copy of MI flights, and then this would be lost typically, so nothing would be changed if we did not have this assignment of an object to the left-hand side of the pipe chain. So because we're creating a new object and storing the result of this pipe chain in at December 25th, it retains the results of what was executed in the pipe chain, in this case, the filtering. But again, to emphasize, MI flights is not being altered. So for example, if we did not have this assignment, okay, we run this code, MI flights is not actually changed, just this temporary copy that has been filtered is just printed. That's all that happens here. So we want to have this assignment happen such that our operation is retained. You can overwrite MI flights with the modified version of itself, although usually I recommend best practice to create a new object if you're modifying a data set, just so that your code is more reproducible and can be run consistently. If you modified MI flights and you keep running this, it can cascade future changes, and you don't want it to depend on like how many times you run the code or what order you ran your code. Okay, by making new objects, the order in which you ran your code is not important, okay, for the most part. So yeah, 2 equal signs for checking equality. A singles equal sign is reserved for specifying arguments inside functions, like the dplyr function, filter. We use 2 equal signs. Yeah, you could have additional arguments. We didn't use extra arguments here, I guess, inside filter. Labs, here's a good example. We use a single equal sign to specify the title argument inside labs, and a single equal sign to specify the y argument. You can use a single equal sign for assignment, although like Hadley Wickham talks about in his book, this is not good practice to do because it kind of conflates argument specification inside functions with object assignment, which are 2 very different things. So even though R technically allows it, it's best to consistently use an arrow for assignment of objects and a single equal sign just for argument specification inside functions. So let's talk about some more complex operations we can use inside filter to subset our data set. So we used a comma to serve as an and for two conditions needing to be true, but you can also use an ampersand symbol if you want to have an or separating two conditions. So you want this or that to be true. You use this, what's called a pipe symbol, which is right above the enter or return key on your keyboard. You can compare variables or numbers to each other using the greater than, less than, greater than or equal to, and less than or equal to symbols. Okay, so all of these are valid operators to use inside a filter to subset our data set. So let's find all flights. Keeping these in mind, let's find all flights that departed in November or December here. Creating this object called November, December. So we can do that by saying month equals 11, or month equals 12. Month is equal to November or December. Okay, if we run that, you can see we had roughly 79,000 flights that left in the month of November or December. If we had more than just 2 months, we wanted to check the flight being in or not. It can start to get tedious and sometimes even far too much to type all that out. Let's say we had, not for the month variable, but maybe we wanted to check if our flight is in a set of, if the planes have a set of tail numbers in a set that has hundreds of flights in it. We don't want to have to list out 100 different ors in a call to filter. So fortunately, there's a in operator that can make checking if a value is in a set of possible values much more efficient. Okay. So let's show how we can use that type of syntax, even though we only have 2 categories here, using the in operator. Copying the code from before, using in, we would say is month in, and then we give a vector of possible values to the right-hand side. So in this case, we're going to make a vector of values 11 and 12. Okay, using the combine function. So now this will return flights. We can see it should be the same. Okay, still about 79,000 using this in operator. Most programming languages have some type of in operator like this, okay, to make this process more efficient. So on the right-hand side, you could have, for example, if you wanted the months 6 through 10, you could have instead the sequence 6 through 10, phi equals 1. And that would give you a vector if you wanted June through October months. Okay, that would be a more efficient way to type this out rather than listing out all these. But here we just wanted November and December. Okay, so we'll leave it like that. Another useful thing to keep in mind when using these logical operations to subset data is to be familiar with De Morgan's laws. Okay, so De Morgan's laws state there's 2 main types of De Morgan's laws. We have the negation of A, so A and B are both logical conditions here. The negation of A or B, so not A or B, is the equivalent of not A and not B. You can think of like this not negation operator was distributed to A, distributed to B, and then it flipped the symbol in between them from an or to an and. The second of De Morgan's laws, so this is De Morgan's first law. The second of De Morgan's laws says the negation of A and B is not A or not B. Again, you can think of it like a distributive property. So this can allow you to construct more complex conditions to help subset your data. And the negation, as a reminder, means that, for example, if we're checking is 3 less than 5, okay, the negation of that, so 3 is maybe 3 less than 5 is one condition, say A. So that's A. B is maybe is 8 less than 4. Okay, so we know A is true, B is false. If we say A or B, is A or B true? That returns true, since at least one of A or B is true. If we say the negation of A or B from De Morgan's laws, that's the same as not A and not B. Okay, and that returns false, since not A is false, not B is true. So not A and not B is false because not A is false. I would encourage you to think about De Morgan's laws for a little bit. And again, thinking about it like the distributive property can be helpful. So let's keep De Morgan's laws in mind to select all flights in this data set that were in the months of November and December using this negation operator. So if we copy the code from before, we can use the negation operator here and be liberal with our parentheses to negate this whole expression. So now instead of keeping months that are in November or December, we're only keeping months that are not in November and not in December. Oh, and I should call this maybe like not December. So we have roughly 385,000 flights that were not in November or December. Okay. Now let's see how we can write code in different ways and how some ways are more readable or understandable than others. So here, let's think about the arrival delay variable gives the number of minutes that a plane arrived after its scheduled arrival, and the departure delay variable gives the number of minutes a plane left after its scheduled departure. So a positive value is corresponding to the plane being late in taking off. A negative value means the plane took off early. Positive value for the arrival delay means the plane arrived late, and a negative value means the plane arrived early. And 0 means right on time. So let's think about what this first set of code returns. Maybe pause the video and think about what these values, what types of rows or flights would be returned from this code before we chat about it. So thinking about De Morgan's laws, negating A or B gives you not A and not B. And note that for the negation of a greater than symbol, greater than becomes less than or equal to. Okay, and same with this greater than as well. So what we end up with is arrival delays that are not less than or equal to, I'm sorry, arrival delays that are less than or equal to 120. In other words, planes that arrived 2 hours or less late, and planes, because this turns into an and planes that departed 2 hours or less late. So planes that simultaneously weren't extremely late in their departure or arrival time. That's what this set of code would give you. And you can confirm that by looking in the using R to get those flights exactly. Kind of like not extremely late flights. If we look at that object and we look at for every flight, their departure delay, okay, it's always less than 2 hours. And the arrival delay for every single one of these resulting flights is also always less than 2 hours. What about this second piece of code? What types of flights do these return? Okay, it's like that office meme where Pam from The Office, to show The Office, shows Michael two pictures. She says corporate needs to have you find the difference between these two pictures, right? They're the same picture. In this case, it's the same sets of rows that are returned. These both have flights that had their arrival delay be less than or equal to 120 minutes, and their departure delay be less than or equal to 120 minutes, with an and in between. Okay, so the comma can serve as an and or an ampersand, like. So these two sets of code return the same exact rows. They give the same result, but they were written in very different ways. This way, I would argue, is much more understandable compared to negating an operation. So in general, of course, whatever you think of first is not a bad route, but I would avoid using negation if you can. If you can write it without negation, some type of condition, because it can be easier to understand. So let's also talk about missing values a bit here. So before running this code, try and think about what should this return? Is a missing value greater than 5? Is 10 equal to a missing value? What's NA plus 10? And what's a missing value divided by 2? So each of these will return either true, false, or NA. They're missing. So if we run this code, okay, all of these return a missing value. Is something that we don't know bigger than 5? Well, maybe. Could be 10, so yeah. Could be 2, so no. We don't know. It's also a missing value. Is 10 equal to a missing value? Well, it could be if that missing value was 10. Might be bigger, might be smaller, so maybe no. So again, we don't know. What's something that we don't know plus 10? Still something we don't know. What's something divided by that we don't know divided by 2? Still something that we don't know. So missing values are, I've seen someone say, contagious a bit in a way, in that if you have missing values playing around with arithmetic operations or comparisons with numeric values, it very often tends to end up with another missing value. Most surprising of all, what happens if you check NA being equal to NA? You may reasonably think that this returns true, but it doesn't. And Hadley Wickham in his book talks a little bit about why. So let's say that Mary has an age and we don't know how old Mary is. And John has an age stored in Y. We don't know how old he is. Are they the same age? In other words, does X equal Y? Well, the answer is we don't know. They might be, but they might not be, right? So it ends up with another missing value if you check NA equals NA. Of course, this might be a little unsettling because if we can't check if an NA is equal to an NA value, how do we know if there's a missing value in our data set then? What if we want to say filter out all rows in the data that had missing values? This is where we have to use the is.na function. This returns true or false, depending on whether or not X has a missing value. So is.na returns true if X has a missing value and false otherwise. So you can use is.na inside the filter function. It's a vectorized function, so it works on a vector of values in here. In this case here, it correctly detects that X had a missing value. So let's, for example, create a new object called MIFlightsComplete where all the departure times are non-missing, and a different data set called MIFlightsMiss where all the departure times are missing. And so let's use the filter function. And dep underscore time gives the departure time. So filter keeps rows where the condition is true. So if we want to return rows where the departure time is non-missing, we want to negate the result of is.na. You might be wondering, well, is there a function that is dot non-missing or is dot not na? Unfortunately, R only has a function called is.na. You could make your own function that detects if something is non-missing, but that function is not available in base R. So we have to negate the is.na function. And then to get departure times that are missing, we just get rid of that negation. So here we can see by running this code that 9,060 flights, which we can recall, that's what Skim showed us earlier in the activity, have a missing departure time, while about 455,000 flights had non-missing departure times. So we could use this to dig in further. Maybe there's systematic things that are true about flights that had a missing departure time. Maybe they're all from the same airport. Maybe they were all like super long or super short flights, for example. We don't know, but this could allow us to explore characteristics about where those flights are missing their departure times.